Hi everyone. In previous lecture, I described for you what is the transfer function of a system and how we can derive the transfer function for a system when we are focusing on a specific output parameter with respect to a selected input source. Today, I want to show you the use of transfer function and how we are going to use them for different applications. The first thing that I want to discuss here is figuring out what is the system output to a given input when we know the transfer function of a system. So here we want to see what is the system output to a given input. So here I'm assuming that I have a system or a circuit, and for this system, I know what is the input to the system. So I know the input in Laplace domain. So what I know is x of s. And also I know the transfer function that describe the configuration and inside of my system. So I know the system's transfer function, which I'm going to show by h of s. Now the question is, what is the output of the system? So what is y of s? So I'm looking for the output to a given input, which is x of s. And I'm assuming that I know h of s. So if I'm looking for the answer in time domain, which is y of t, I need to know y of s, and then I can apply Laplace inverse and find my answer in time domain. The question is that what is this y of s? The transfer function can help me here. I know that the transfer function describes the relationship between the output and the input in Laplace domain. So it means that if I'm specifically looking for y of s, then it's going to be equal to h of s multiplied by x of s. So if I know my input and my transfer function, I can multiply them in Laplace domain, and that describes the output in Laplace domain, and then I can use this output in Laplace domain and apply Laplace inverse and find my answer in time domain. However, before applying Laplace inverse, what I need to do is I need to do PFE, and then PFE will break my fraction into partial fractions, and then Laplace inverse is going to be easier. So I need to do PFE. Now let's focus on PFE and see what do we have in this PFE. PFE basically just will add one single partial fraction for every single root of my original fraction, which is the result of multiplying h of s by x of s. So I'm going to have some root which are the result of having h of s, and then I'm going to have some other root which are going to be in my answer because of x of s. So if I do the partial fraction, what I'm going to see is something in this form. I'm going to have, for example, k1 over s plus p h1, and then k2 over s plus p h2. So what is ph1? What is ph2? ph1, ph2 are different roots that are in my answer because of h of s. And then I'm going to have, so these are basically because of h of s, and then I'm going to have some other roots. I'm going to show them as ka over s plus px of a, and then some other root. So as you can see, I'm going to have a PFE which has two sets of partial fraction. The first set is the result of the roots that I have in the denominator of h of s, and the second set of roots are the result of x of s, so the result of the roots that I have in x of s, which is my input. Now something that you need to notice here is that these roots, the roots of h of s, will determine the natural response of the system. So here you're going to see the natural response of your system. And then because of the roots that are coming from your input, you're going to have some portion in your answer which shows the forced response, or in another word, the response to the input. So here, because of these roots, which are the result of x of s, we are going to have forced response, or our response to input. So let me review what we discussed. As you can see, our y of s, or our answer in Laplace domain, have some roots. Some of them are because of h of s, and some of them are because of x of s. Those roots, which are the result of having h of s, will produce the natural response of the system, and the other set of roots, which are the result of x of s, will produce the forced response, or the response to the input for this particular answer. Now, it should make sense here that h of s is showing you the configuration of the system. So whatever you get because of h of s is basically the natural response of the circuit or the system itself, and it doesn't have anything to do with the input. And then the other set is the forced response, and you have that particular response in your system because of applying this particular input. So if you change your input to another input with different roots in its denominator, you're going to have a different answer here. Okay, now I want to use what we discussed here to look at and to see how we can analyze the steady state response of a system or circuit into sinusoidal input. So what we want to discuss here is the steady state response to sinusoidal input. Okay, so we have a circuit. Let's assume that we know what is the h of s for the circuit. And whenever we apply a particular input to the system or to the circuit, what we get as y of s is our total response in Laplace domain. It means that if you apply Laplace inverse to this response and describe your answer, your response in time domain, this y of t is your total response. So what we have as here as y of t is our total response. What does it mean? It means that it has two components. So it has the transient response plus the steady state response. So if you break this response into two main terms, part of it is transient, which would die after a while, and part of it is a steady state response. So it remains in your circuit no matter how long you're far from the time you've applied the change. For example, let's assume that you have a response like this. Then what you have at the end is your steady state response. And the way that you reach to this steady state response describe your transient response. So something will happen at the beginning in order to reach to the final or steady state response, and that's what we call as our transient response. Now let's assume that we are looking specifically for transient response. For steady state response. So this is our goal. We are not interested in the transient response. We just want to know what is the steady state response of the system when we are applying a sinusoidal input. So our input is, for example, a cosine of omega t plus theta. So we are looking for a steady state response, which is here, and we are assuming that the input is sinusoidal. Why we are focusing on this particular one? Because when later we are going to talk about filters, and in filters we have different type of frequency being applied to the circuit. So it means that with filter our focus is on sinusoidal input, and our desired part of answer is about the steady state response. So these two are very important for us. So this is a particular situation that we want to learn about in more detail, and we are not focusing on the general situation. So right now you know how to solve in general form. So for whatever input you have, and assuming that you are looking for the complete response. But here, let's see what we can do if we are looking for the steady state response when our input is sinusoidal. Okay, let's see what are the possible approaches of solving this scenario. The first one is very simple. What we can do is that we can find the total response here. So we can go through the general rules, and what we can do is that we can find complete response. And then throw away the natural response or the transient response. And then we can remove or throw away our transient response. So basically what I'm saying here is that you can say that your y of s is equal to your x of s multiplied by h of s. Then when you have your y of s, the next step is that you can calculate your y of t, which is the Laplace inverse of y of s. And finally, you can say this y of t has some component that are transient, and the rest of them are steady state. So you can throw away the transient part and keep the rest as your steady state response. That's the general approach. In this approach, you're solving for the total response, which is longer and bigger than your steady state response. So you're going to deal with a lot more calculation, and it's going to be a longer path in order to solve for steady state response. For example, let's assume that at the end, you have something in this form. Y of t is equal to, for example, 10 e to minus 2t cosine of 10t plus 2 sine of 3t. So here what you can see is two different terms in our final response or our total response, and this portion is basically our transient response. Why? Because this e2 minus 2t will damp finally, will die after a long time. So this part is basically showing you the transient response of the system, but the other portion does not have any dying factor. So it will remain in the circuit, and that's your steady response, steady state response. So this is one approach that you can solve your circuit, and then in general, and then what at the end in your response, you can throw away all those terms with transient portion and then keep the steady state response. I'm going to show you the other approaches in the next lecture.